Okay, so we have this situation like A is equal to S lambda S inverse. What can we do with this? Let us find out what is A square is. A square is S lambda S inverse uh, square, or let me write it S lambda S inverse times S lambda S inverse. So this actually, uh, when I open up this parenthesis, this one, this part is nothing but I. So S lambda I lambda S inverse. So lambda times I or I times lambda, that doesn't affect much. So that I can write it as S lambda, or in other words I can write it as A square is equal to S lambda square S inverse. Or if I generalize this one, this is actually A to the power K for any positive value K, for any value of K in fact, S okay. So if we have, say for example, we have the okay, that's it. uh, okay, let us say we have a situation like A is equal to A A B B A, and you are asked to find out what is A to the power n. So that can be written as A to the power n is equal to. So here you have eigen vector matrix, eigen value matrix, and inverse of eigen vector matrix. So what is the uh, eigenvalues of this A, B, B, A, this particular matrix? Can you find that out? Now, in another way, if you see this one, square root, we are finding plus minus, so another lambda would be a plus b. So in that way, if you go, this is actually that is my lambda matrix, right? And what about the eigenvectors? And its inverse 1 upon 2. To find the inverse, you'll get this one. So what about this one? This eigenvalue matrix raised to the power n. So as all the off diagonal elements are 0, so I have the values as a plus b to the power n and a minus b to the power n. So that actually becomes a to the power n is equal to half 1, 1, 1 minus 1. A plus b to the power n, 0, 0, a minus b to the power n, 1, 1, 1 minus 1. If I multiply that further, so that becomes a plus b to the power n, yeah, that is 0, and again a plus b to the power n and this one a minus b to the power n, and this one is minus a minus b to the power n. Yeah, that's it. So this is equal to 1 upon 2 a plus b to the power n plus a minus b to the power n. A plus b to the power n minus a minus b to the power n. A plus b to the power n minus a minus b to the power n. A plus b to the power n plus minus into minus plus a minus b to the power n. That is what a to the power n is. Okay. So just a quick recap. A is equal to s lambda s inverse. So in order to find its square, we multiplied it 2 times. S inverse s, that is nothing but I. So that's what I am writing here. A square is equal to s lambda square s inverse. And if we extend to any value of raised to the power, let it be k. So a to the power k is equal to s lambda to the power k s inverse. And an example we have taken a b b a, and what is a to the power n? This is what we are getting. Okay. So
Hello, sir.
okay. We'll start with another topic today.
Hello, sir.
Yes.
Sir, why do we put half while calculating a to the power n?
Can you find the eigenvector there?
Okay, yes, sir. That's part of eigenvector.
Scalar quantity you will get. Okay. Now let us go to another important part of this is symmetric matrix. Symmetric matrix, or so to say, S is equal to S transpose, right? S is equal to S transpose. Now, whenever you find eigenvalues, eigenvectors of a symmetric matrix, S, what thing you get actually. In fact, our subsequent discussions would be on symmetric matrices only. So they hold some beautiful properties. So let us see them. Number one is all eigenvalues of just this is not responding properly. All eigenvalues of a symmetric matrix are real numbers. And another important property is all eigenvectors of a symmetric matrix are, let us not write R, can be uh, orthogonal. No, if it can be orthogonal, then they can also be orthonormal. So, orthonormal. Yeah, this can be, that is something bothering. What this can be is actually. Yeah. Can be is actually eigenvalues of symmetric matrix are real. But then when it comes to eigenvectors, uh, let us say, for example, we have a symmetric matrix S, which is equal to I, let us say. Okay. So I is identity matrix. So what are the eigenvalues of this S? All the eigenvalues lambda are 1. That's right. Or in other words, I can write as okay, eigenvalues are 1. All the eigenvalues are 1. So what about eigenvectors? Eigenvectors are I times x. Let me write this x. I times x is equal to lambda times x. and lambda is nothing but 1. That's right. Now you have lambda as 1 and here it is x. That means you can choose x whatever you like, isn't it? You can choose x whatever you like. So, well, if you have been bestowed with the power to choose whatever x you like, it's better to be judicious and choose x in such a way that they are all orthogonal. So you have a plane of vectors, you have a sea of vectors. Now, from those vectors, from that sea of vectors, you choose very judiciously all those vectors, all those eigenvectors. Here the vectors are x, here as per the equation, it could be any vector, but then so that they all becomes orthogonal. Now, once you have chosen it to be orthogonal, they can easily be made orthonormal, divided by their length. So that is why it has been written as it can be. You can choose it to be orthogonal. Okay. So, and so these eigenvectors x or orthonormal eigenvectors, we write it as q1, q2, and so on. So the famous equation that we wrote in the above, A is equal to S lambda S inverse, can now be written as A is equal to Q lambda Q inverse. That's right. But at the same time, we also know that what is Q transpose Q? What is Q transpose Q? We have Q1, Q2, Qn. Q transpose Q. What is this? This is nothing but the identity matrix, right? All the off diagonal elements are 0. So to say, I can also write it as Qi transpose Qj is equal to 1 whenever I is equal to j. it's equal to 0 whenever I is not equal to j. Okay. Yeah, so basically it's q transpose q is equal to I, or q transpose is equal to q inverse. So this equation now becomes A is equal to q lambda q transpose. This is known as spectral theorem. And remember, what are Qs? This is an eigenvector matrix which are orthogonal. Okay. Okay. Let us prove something. Like let us say Sx is equal to lambda x. That is one eigenvector x. And let us also consider another eigenvector Sy is equal to 0 y. So I have, well, eigenvalues could be 0, so no issue with that. I have two eigenvectors x and y. So if you recall our first few classes, uh, can we say, according to that, that y is in the null space of S, and x is in the column space? Yeah, y is in the null space of S. That is quite understood. Sy is equal to 0. But what is x? X is uh, nothing but 1 upon lambda times Sx. And it's a combination of the columns of S. Lambda is a scalar quantity, right? 1 upon lambda is also a scalar quantity. So ultimately it becomes Sx is the governing term. So it's a uh, linear combination of all the columns of S. But then one thing we are forgetting here, it's symmetric. but S is symmetric. So if S is symmetric, can we write that column space of S is equal to row space of S? Hence, yeah, not hence. We also know that row space and null space are orthogonal. That means Y and X are orthogonal. Okay. Now this one we just it was a cakewalk actually, just to so that lambda is one of the eigenvalues, 0 is another eigenvalue. So x is the corresponding eigenvector of lambda, y is different from x, and we prove that. But then what if we don't have lambda equal to, I mean the eigenvalue is not equal to 0, it's something else. So let us take another eigenvalue, s y is equal to alpha times y. It's another different eigenvalue, which is not equal to 0. So can we proceed in this direction? Um, a minus lambda I x, yeah, that direction. S minus alpha I y is equal to 0 y. S minus alpha I x is equal to lambda minus alpha x. Okay, this lambda minus alpha should not be equal to 0 again, otherwise things would be same. So now what? Y is in the null space of S minus alpha I. X is in the column space of S minus alpha I. Again, the same thing. Y transpose X equal to 0. And this is again in the case Y and X are different. Okay. So that is how to prove this one. And there is another proof also. This is the second part only for the orthogonal. What about for the real number? That symmetric matrices have real eigenvalues. Okay, I'll leave it to that that to you. Uh, it's actually with respect to the complex numbers. It would be easier to prove. Like I'll just the other part is Sx is equal to lambda x. So what you do here is find the complex conjugate of x, the conjugate x is equal to x bar, and its transpose is x bar uh, and its transpose. That you pre-multiply with this s x is equal to x transpose. Remember, I am not writing minus t, okay? This I can write it as I can take lambda first because it's a scalar quantity. Yeah. Now just look at the right hand side. It is some scalar quantity. Lambda we have already, sorry, it's a scalar quantity. Hmm. Okay, how do we prove this? How do we prove this? Now, this is where we are. We can we need to prove that lambda is real, right? Lambda is real. This is possible uh, in order to prove lambda to be real, um, we need to prove LHS and RHS are real. If LHS and RHS are real, then we can easily conclude that this one is lambda is a real number. So I leave that up to you. It's quite easy one, in fact, from here. X transpose X, that's actually when you multiply, how that turn out to be. And one more hint here, even if X is a complex number, let us say A plus IB, and its complex, its conjugate is A minus IB, and when you multiply these two, A minus IB, A plus IB, that is A square minus B square, A square minus IB square, so that becomes A square, I square equal to minus 1, so that becomes plus B square. So when you are multiplying these two, you are actually getting a real number. Yeah. So that is what the hint is. You can try out with this. And that's all. That's all for today. See you in the next class.
Hello, sir.
Yes.
So the last few classes in the Monday channel couldn't be downloaded, sir.
Let me check. In fact, I haven't downloaded even a single one. I thought you guys could be downloading. Let me check. By the way, you can access the whiteboard, right? Can you access the whiteboard? Hello?
Oh, sir. Yes, sir.
Can you access the whiteboard?
So we can only see the whiteboard.
Yeah, that is what I meant to access. You can download it, right? I mean, you can copy the entire thing.
No, sir. How do we do that?
Okay, just tell me, can you browse through the whiteboard right from the first class to the present class?
No, no, sir. We can't do that.
Okay. Uh,
Sir, actually, in the some beginning classes, we could access the whiteboard, but not from a long time.
you're not able to access the whiteboard. Are you mean to say you're not able to see whatever I'm writing?
So we can see only the current page you are in. When you scroll down, we can't see the pages that you have left above.